Hello, welcome back to SCI Teach. So this is chemistry revision. We had done in the previous videos SS1 topics and we've completed SS1. Now we're going to start SS2 chemistry. So go along with us and revisit chemistry SS2 topics one by one. Remember to subscribe to this channel, like and share the videos to your friends who are writing exams or are preparing for exams or who are in SS2 as well as SS1 and SS3 so they can prepare to ace their exams. Alright, so let's go. The first topic is periodic table. Remember, this is a revision. We're going to touch the areas exam come out from, and then we're not going to dwell much on the details. We're going to touch all areas that are important for exam purposes. So periodic table. You know that the periodic law states that the properties of the elements are a periodic function of their atomic number. What it means is that the elements in the periodic table are arranged in order of their increasing atomic number. Okay? And we remember atomic number is the number of protons in an atom. Okay? Alright, so it's Mendeleev that developed and created this periodic table in 1869. And he divided the elements into groups and periods. So there are 8 groups and 7 periods. The 8 groups are vertically arranged, columns, and they call them groups. And the 7 periods are horizontally arranged, and there are rows. The other ones are columns, these are rows. Now the groups are numbered from 0 to 7. That's what I mean, is from 1 to 7 and 0. That's group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 0. Group 0 is group 8. They're called 0 because they don't need to gain or lose electrons to form a stable octet. They're already stable. They are royalty. They are kings. They are noble gases. Now, elements in the same group have the same number of electrons in their outermost shells. And we know the outermost shell is what is called valence shell. So elements in the same group will have the same number of electrons on that valence or outermost shell. And these electrons on the outermost shell, the electrons on the valence shell, is called the valence electrons. That means group 1 elements, all the elements in group 1 will have 1 electron on their outermost shells. Group 2 elements have 2 electrons on the last shell. Group 3 have 3 electrons on the last shell, like that till group 8, which have 8 electrons on the last or valence or outermost shell. Now, okay, apart from the 8 main groups, there are the transition group of elements. Transition elements, they are metals, and they lie between group 2 and 3 of the periodic table. All right. Now the periods are arranged from 1 to 7, and elements in the same period have the same number of electron shell. How many shells an element has can be known if you know the period in the periodic table that element falls under. Because if an element is in period 1, then it has only 1 shell. That's why hydrogen and helium are the only elements in period 1. Elements in period 2 will have 2 shells. That means they will have at least 3 electrons, because 2 electrons only are contained in the first shell. If you have more than 2 electrons, then you need another shell to start carrying the third and the fourth till 10. So elements in period 3 will have 3 shells, period 4, 4 shells, period 5, 5 shells, till period 7, 7 shells. So among the elements in the period 6 and 7 are the elements of the lanthanides and the actinide series. So we have another set of elements called lanthanides, and we have another one called actinides. They are known as inert transition elements. You want to know, inert means non-reactive. They don't react. Now, we have also in the divisions in the periodic table, we have metals, we have metalloids, we have non-metals. So the periodic table shows the diagonal divisions of the elements into metals and non-metals. So the metals are found on the left-hand side of the periodic table, and the non-metals on the right-hand side of the periodic tables. Then the metalloids, semi-metals, they occur on the boundaries of the metals and the non-metals. Alright? Now in the periodic table, we can also see electronic configuration. What I mean is the S, P, D, and F blocks. Okay? Now group 1 and 2, the metals, they make up the S block elements in the periodic table. And they are called alkali metals. Alkali metals for group 1, alkaline earth metals for group 2. So the metals in group 1 and 2, the alkali metals and the alkaline earth metals make up the S block. Okay? And then group 3 to 7 and 0. Group 3, 4, 5, 6, 7, 8, which is 0, they form the P block elements. That's because electrons are added progressively to the p orbital as well as the s orbital. Okay, so in addition to the s orbital, they have p orbitals, and electrons are added to those p orbitals as we move across the table from group 3 to 7 and 0. Then the transition elements form the d block. Same thing, because it can be an exam question. You can be asked to explain reasons why you say that transition elements or non-metals or metals are found in the D, P, or S block respectively. So I'm saying now the transition elements form the D block because they contain the D electrons in addition to the S and P electrons. Okay? What I mean is this: the S block elements, the metals group 1 and group 2, have only S shell, so they contain only S electrons. But the non-metals group 3 to 7 and 0 contain P block in addition, or contain P electrons in addition to the S electrons. The transition elements contains D electrons in addition to the P and S electrons. So lastly, the lanthanides and the actinides form the F block. Now we completed S, P, D, and F. They form the F block because in addition to the S, P, and D electrons, F electrons are added. Right? Now also remember that there are some trends, periodic properties of elements in the periodic table. So what is periodic property? WAEC likes asking. Periodic property is defined as any property, whether physical or chemical, of an element which changes regularly, which shows variation with increasing atomic number. The properties that elements in the periodic table have, which will change as the number of protons is increasing, which will change with increasing atomic number. Now let's look at examples of these periodic properties so you understand, like atomic and ionic size. Atomic size or ionic radius, or radii, let's put it that way. Now the distance between the two nuclei of covalently bonded atoms is called atomic radius. Now generally, the size, atomic size decreases across the period and increases down the group. So you'll be asked, atomic size, what are the trends? The trend is that atomic size will decrease across the period. As you are going from left to right in the periodic table, atomic size will be decreasing. The atomic size of metals is bigger than that of non-metals. And this is not the same for ionic radius. So we have atomic size decreasing as you go across the period from left to right, but increasing as you are going from top to bottom, down the group. So if you are moving in group 1, from the hydrogen down, will not ascend across, the atomic size will be increasing as you are going down. But if you are going from left to right, that's in periods, from hydrogen to helium, okay, from sodium to neon. If you are going like that across from left to right, then the atomic size is decreasing, reducing in size. That's the atomic size is a periodic property, because you see, as an atomic number is increasing, something is changing. The atomic size is changing, is showing variation. And we said periodic properties are properties that show variation. They change regularly when the atomic number is increasing. So atomic size or ionic radius is 1. The second periodic property is ionization energy. That's ionization potential. Now this one is the energy required to remove a valence electron from a gaseous atom to form an ion, right? Take note that ionization energy is always positive. And what is the trend? What is the periodic property? Or what's the variation it shows? Ionization energy increases across a period. Remember the explanation. I'm not going to go deep into that again because I've already explained. Ionization energy increases across the period and decreases down the group. Okay? So if you may be asked, the ionization energy of an atom is affected by what factors? The first one is the distance of the outermost electron from the nucleus. It's important to note that the further away from the nucleus a shell is, the easier it is for electrons on that last shell to be removed. Remember we said ionization energy is the energy required to remove a valence electron. So if you have like 5 shells, that means that last shell is very far away from the nucleus, at least further away than the fourth shell and the third and the second and the first shells. It's going to be easier to remove the electrons on the last shell compared to the fourth shell, compared to the third shell and the second and the first shell. So ionization energy is affected by the distance of the outermost electron from the nucleus. The electrons on the outermost shell is the outermost electron. And since that outermost shell is further away from the nucleus, then it's easier to remove the electrons on that shell. So the distance of the outermost electron from the nucleus is 1, and then another one is the size of the positive nuclei charge. The size of the positive nuclei charge, the center, and then the third one is the shielding effects of the inner electrons. So the inner electrons shield the positive charge in the center from getting to the next shell, and the ones that get to the next shell is shielded from getting to the next shell, and that's why the next or further shells become weaker because they are not that attracted to the positive nuclear center as the first shell is. Now the next periodic property is electron affinity. So ionization energy deals with loss of electrons, but electron affinity deals with the gain of electrons. So electron affinity can either be positive or negative, but the negative value is usually larger because when a negative ion forms, a lot of energy is given off. So what's the trend? Generally, electron affinity increases across the period from left to right, except group 0, group 8. Remember, because they are noble gases and they are stable already. So they won't need to gain electrons. And remember, electron affinity deals with gaining of electrons. So electron affinity increases across the period from left to right, except for group 8 or group 0, because they are noble or stable gases. And then it increases down the group as the atomic radii decreases. And the fourth one is electronegativity. Electronegativity is the power of an atom in a molecule. So it's a measure of how an atom competes for electrons in a bond. Okay, so the higher the electronegativity, the greater its ability to gain electrons in a bond. And what is the trend? Electronegativity increases across the period but decreases down the group. The next one is metallic property. That's electrical or thermal property. And this is the ability to conduct electricity. Of course, metals conduct electricity and non-metals don't. So generally the metallic properties increases down the group and decreases across the period. As you're going from left to right in the periodic table, across the period, you are going from metals to non-metals. So it should be decreasing because metals have more metallic properties than non-metals. Okay? So when you want to state down one, say the metallic property increases down the group and decreases across the period. Increasing down the group because even when you are dealing with non-metals, so you're going down the groups, they meet metals. So metals are below. Okay? Now we have melting and boiling points. So melting destroys the arrangement of an atom. in a solid. Okay, so different groups exhibit different trends in melting and boiling points. So when you get to melting and boiling points, you're not going to say generally, you're not going to deal with it generally, you're going to class it into groups. Group 1 and 2 are metals, so you know that metals have high boiling points, right? Or melting points, sorry. So melting and boiling points will decrease down the group in group 1 and 2. But for the transition metals, they will increase down the group, melting and boiling points. For group 3 and 4, melting and boiling points will be decreasing down the group, and group 5, 6, and 7, melting and boiling points will be increasing down the group. So in summary, we are saying that melting and boiling points for metallic elements, group 1 and 2, decrease down the group and increase across the period. So on the other hand, for non-metals, that's group 5, 6, and 7, melting and boiling points will increase down the group and decrease across the periods. So we move to the next topic, chemical reactions. Chemical reactions are the processes by which chemicals react to form new chemicals, and these new chemicals are with different compositions. So the substance which undergo the chemical change, they are known as reactants, while the new substance formed is called a product. So we can say a chemical reaction is a process where reactants are transformed into products, converted into products. There are different types of reactions. We have combination reaction. That's when two or more substances combine to form one single compound. Okay, so that's a combination reaction. That's like Fe plus S will yield FeS. Iron combined with sulfur to yield iron sulfide. The second one is decomposition reaction. Combination is joining together. Decomposition is breaking apart. So a single reactant is decomposed or broken down into two or more products. And when heat is needed to bring about this decomposition, we call it thermal decomposition. Heat, thermal. Just like limestone, CaCO3, can be broken down to calcium oxide, CaO, and carbon dioxide, CO2. Okay, that's decomposition reaction. Then we have displacement reaction. And in this type of reaction, a free element replaces or is substituted for one of the elements in a compound. So the free element will be more reactive than the one it replaces before that can happen. Okay, I have zinc plus copper sulfate, that's Zn plus CuSO4, would yield copper. Now copper comes out, and the free zinc element that was combining with it forms a bond with the sulfate. So instead of CuSO4 now, it's now ZnSO4, and copper now stands out when zinc was the free element before. That's because copper is more reactive than zinc, and copper displaces that zinc and takes its place to form a bond with the sulfate to become zinc sulfate. Then the fourth one is double decomposition, or we call it double displacement, or in a rare case we call it metathesis. Now, this is a reaction in which the positive ions and the negative ions in two compounds switch partners to form new compounds. This is what I mean. Let's say we had AgNO3. Remember, Ag is with NO3, and it's combining with NaCl, salt. Na is with Cl. If they undergo double decomposition or double displacement, then what will be formed is AgCl. Ag was with NO3, but Ag will now bond and form with Cl of NaCl. So that means Na will now go and bond with NO3. So the product is AgCl plus NaNO3. What I'm saying is we had Ag bonding with NO3, AgNO3 plus NaCl. When it yields AgCl, that means Ag now took the partner of Na, which was Cl, and bonds with it. So Na will take the partner of Ag, that was NO3, and bond with it. Okay, that's double. So two of them switch partners 2 times, not like the displacement where just one free element take the other one. The other one can't take its partner because it didn't have a partner, it was free. But in double decomposition, both of them had partners but switch partners. Don't practice this in real life. Okay, now number 5, catalytic reactions. This one generally. A catalyst is a substance used to speed up or slow down the rate of a chemical reaction. So this process, that's catalysis, is important in some reactions. So any type of chemical reaction that uses a catalyst is a catalytic reaction. Okay, but example of catalyst is nickel. Acid sometimes are used, and a lot more. Now let's go to rate of reactions. Rate, when we say rate, it means how fast. Okay, so this is the number of moles of reactants converted or product formed per unit time. It's important. It is the measure of the change in concentration of the reactants or the change in concentration of the products. So we can say that the formula for rate of reaction is change in concentration of reactants or change in concentration of products all over time taken for such a change. Okay. Now take note, the concentration can be in form of mass, can be in form of number of moles. So depending on what the question gives you, the rate will always be the change in concentration, can be in mass form, but all over time taken. Take for instance, if a question is asking you that and gives you maybe a certain grams of maybe limestone, and it was added to excess maybe dilute acid, and carbon dioxide was evolved, and they tell you the reaction takes about 5 minutes, they should calculate the rate of reaction. Now, so you write rate of reaction is concentration all over time taken, but concentration now is in form of mass because you were given grammage. So you say mass of that reactant all over time taken, and you will have your answer. It's easy to solve rate of chemical reactions. Now we visit collision theory. The collision theory states that the rate of reaction is proportional to the number of collisions between the reactant molecules. So the more often reactant molecules collide, the more often they react with one another, and the faster the reaction rates. So in reality, only a small fraction of the collisions are effective collisions. What I mean effective collisions are those collisions that will result in a chemical reaction. Let me take you back. It's like this. Collisions lead to chemical reactions. So the reactants, how they react is that they collide with each other. Now, if they need to collide and collide till they form, there's a particular collision that will have enough energy called the activation energy to become a product, to react and become a product, then those collisions are going to take more than one, twice. So that means if you want a reaction to take place faster, you need the collisions to be more. Okay, we're going to see that in conditions for chemical reaction to occur. So number one, two molecules must collide in order to for them to react. Then number two, the colliding molecules must have enough energy to react. So the amount of energy that is enough to initiate the reaction is what I called activation energy. So it's not enough for the two molecules to collide. They must collide and have enough energy called activation energy before they can react and form a reaction. Now, the molecules must collide in the proper orientation for the reaction to occur. Something about the double bonds and the triple bonds and stuff like that. So, in summary, the collision theory explains the reaction rate in terms of the frequency of their reactants. Reactants have to collide and do so in certain conditions of activation energy and the right or proper orientation. What are the factors that affect the rate of reactions? Very important. Number one, nature of reactants. Number two, concentration of the reactants. If they are gases, then we're not dealing with concentration, we're dealing with pressure. And then number three, surface area of the reactants. And then number four, temperature of reaction, mixture, pressure of light, presence of light, and presence of catalyst. Okay. Now there are videos in the lecture playlist where you can go into these topics one by one to go into deep details of each of them to explain every single thing. This is a revision, so you can revisit that. Okay. Now we get to the next topic, mass and volume relationship. Now this is a very tricky topic for students but it's going to look very easy if you go to the lecture playlist and listen to a very concise video I made about it. Very interesting, and there is no way you listen to it and you don't have full knowledge and understanding of this topic. So I'm going to try and revise it in such a way to wake your memory for you to be able to learn that topic or understand the topic's concept. So mass and volume relationship. Now, mass and volume relationship is a relationship formed between two species in stoichiometric problem solving exercise, where the mass of one of the species and the volume of another species is the basis of the relationship between them. So the species for which volume is the basis of connection should, be preferably a gas or a solution, provided that if it's a gas, then a gas law is used, like the ideal gas or the general gas equation. But if it's a solution, then the concept of concentration in terms of normality, molarity is what we're going to use. But we're going to first of all make sure we balance our equation, because we need to know the correct number of moles. So a balanced equation is very important to solve mass and volume relationship. Okay. Now, mass and volume relationships take steps. They can give you mass to mass. They can give you mass to mole. All right. So mole ratio and mass relationship is there inside mass and volume relationship. Okay. So you have to find the number of moles and connect them to what you are looking for. Remember, you're going to give two species. Okay, not two species. You're going to be given an equation, maybe in statement form, and you form it into an equation. You balance it, and then you'll be given either the mass or number of moles or volume of just one species. And you're asked to use that and find either the mass or number of moles or volume of another species. So you have to use the mole ratio of the reaction and compare the one that is given to the one you are looking for. And from there, you can do necessary conversion by changing mass of the given species to number of moles. And then if we're asked to find the number of moles of the other species, you use the mole ratio to compare it with the other, and you will know your answer. Or if you are asked to find volume, you multiply the number of moles by 22.4 dm cube, and you have the volume of the species you're looking for after comparing with the mole ratio. Or if you're asked to make or find the mass also of that unknown species, then you still use number of moles equals to mass over molar mass and make mass subject of equation and find the mass of the new species. That's a full summary of that topic. It's not difficult. Go to the video in lecture playlist. You see the topic mass and volume relationship. Watch it and thank me later. Okay. Now we move to energy and chemical reactions. Now, due to the absorption of energy when chemical bonds are broken and the release of energy when chemical bonds are formed, what I'm saying is that when you break a bond, the different reactants that form back from the compound that you break down will gain energy, heat energy. But if you form a bond, they lose that energy to have a complete bond set. So I'm saying due to that absorption of energy when chemical bonds are broken and the release of energy when chemical bonds are formed, chemical reactions almost always involve the change in energy between products and reactants. Now, by the law of conservation of energy, the total energy of a system should remain unchanged. That energy should neither be created nor destroyed. So it's important to know why they will release energy or absorb energy. So let's look at exothermic reaction to get more knowledge. Exothermic reaction releases heat and light into the surrounding. Example, combustion reactions are usually exothermic. And in exothermic reaction, the products have less enthalpy. And as a result, an exothermic reaction is said to have a negative enthalpy. It's losing heat, so it's negative. Okay. Now, Now what this means is that the energy required to break the bonds in reactants is less than the energy released when new bonds form in the product. So the excess energy from the reaction is what is released as heat and light. Okay? Now, endothermic reaction will absorb heat and light, or lights can absorb heat alone and or with light, or both of them. An example is decomposition reaction. They are usually endothermic. So in endothermic reactions, the end products have more enthalpy than the reactants. So the endothermic reaction has positive enthalpy of reaction. We deal with energy changes. The change in the heat content during the reaction is the difference between the heat content of the products and that of the reactants. So you can write a formula: change in heat equals to heat content of product minus heat content of reactants. That's change in heat equals to HP minus HR, heat of reactants, minus heat of product minus heat of reactants. And change in heat is negative for endothermic reaction, remember? And change in heat is positive for endothermic reaction. I'm saying change in heat is negative for exothermic reaction, while change in heat is positive for endothermic reactions. So let's see the different heats changing enthalpies. We have heat of formation. Okay, heat of formation. The amount of heat evolved or absorbed when a substance is transformed is known as the heat of formation or enthalpy of formation. So if you're dealing with the standard heat of formation, then we are dealing with the heat evolved or absorbed when 1 mole of a substance is formed from its elements under standard condition. Then we get to heat of neutralization, and the amount of heat evolved or released or given off during a neutralization reaction in which 1 mole of water is formed is known as heat of neutralization, or you call it enthalpy of neutralization. If you're dealing with the standard heat of neutralization, it is the amount of heat evolved when 1 mole of hydrogen ions, H+, from an acid reacts with 1 mole of hydroxide ions, OH-, from an alkali to form 1 mole of water under standard conditions. So total heat evolved will be mass times specific heat capacity times temperature rise. And we get to heat of combustion. The amount of heat that is evolved when 1 mole of a substance is burnt completely in oxygen is known as heat of combustion or enthalpy of combustion. Now, the standard heat of combustion of a substance will be the heat evolved when 1 mole of a substance is burned completely in oxygen under standard conditions. Now, why I'm defining heat of whatever and then the standard heat of that thing is because WAEC can either ask you to define the heat of either combustion of or any other reaction, or the standard heat of that reaction. Okay, so it's important to note the difference between the heat of combustion and the standard heat of combustion. So heat of combustion is determined using a bomb calorimeter. An objective question for you: use a bomb calorimeter to determine the heat of combustion. Okay, now heat of solution is the enthalpy change associated with the dissolution of a solute in a solvent at constant pressure. Dissolution, dissolve something. Okay, so the standard heat of solution is the amount of heat absorbed or evolved when 1 mole of a substance is dissolved in so much water that further addition of the water will result in detectable heat change. Take note of that dissolution, dissolving something, dissolution is exothermic if the lattice energy is less than the hydration energy. But dissolution is going to be endothermic if lattice energy is greater than hydration energy. Remember this, that in hydrated salts, that's where the ions are already hydrated before dissolution, the heat of hydration will be very small. So the dissolution of hydrated salts will be endothermic. Alright? Let's differentiate between bond energy and lattice energy so that we understand the lattice energy I was talking about. The strength of a bond is measured by the amount of energy required to separate the atoms or the ions that are held together by the bond. And that's what we call bond energy. Okay, so this is the energy that is absorbed when a bond is broken or evolved when a bond is formed, the bond energy. But the lattice energy of an ionic crystal is the change in heat or formation of 1 mole of an ionic compound from widely separated gaseous ions under standard conditions. So bond energy helps us to understand the stability of molecular covalent substances, while lattice energy helps us to understand the stability of ionic crystals. That's the difference. It's important to also take notes of spontaneous and non-spontaneous reactions. Spontaneous means it can happen without any help. So a spontaneous process is capable of proceeding in a given direction without needing to be driven by an outside force, an external force. Example, you spray a perfume in one corner of the room, it will diffuse to other corners of the room. You don't need to push it. That's a spontaneous process, spontaneous reaction. Ice melting in warm water, put ice in water, it will melt. You don't need to stop it. Or you just bring it out to the environment, it will start melting slowly. That's spontaneous. Salt dissolving in water, you put salt in water, you don't need to do abracadabra, it will melt. It will dissolve, sorry. And that's spontaneous. Iron rusting, it's spontaneous. Iron will rust as long as you're keeping. I'm not talking of aluminum. Aluminum is not iron, I mean iron, Fe. So, the more the iron content in metals, the more it's susceptible to rusting. Now, most exothermic processes occur spontaneously. Some endothermic processes, however, can also take place spontaneously, like crystals of ammonium trioxonitrate 5 will dissolve spontaneously as it absorbs so much heat. But enthalpy is not the only factor that determines the spontaneity of a process. Other factors include entropy and free energy, or we call it Gibbs energy. So you'll be asking yourself, what is entropy? Entropy is a property of a substance that is a measure of the system's thermal energy per unit temperature, which is available for useful work. Simply put, entropy is a measure of degree of disorder or randomness of a substance. So entropy measures how disorderly or how random a substance is. A perfectly ordered system at 0 Kelvin will have an entropy of 0. At 0 Kelvin, all the particles are bonded. They're in one place. They're not disordered. They're not moving randomly. So you have a perfect ordered system when you have a substance at 0 Kelvin temperature. Change in entropy is entropy as symbol S. So change in entropy is change in heat all over time. Then I said something about free energy or Gibbs energy also. The free energy of a chemical system is the energy which is available for doing work, useful work. So we've talked about entropy and free energy. But take note of this about entropy. The total change in entropy is equal to change in entropy of the surrounding plus the change in entropy of the system. Change in entropy is change in S. Remember, entropy is S. And for a chemical change to occur spontaneously, change in S, that change in entropy, total change in entropy, must be positive, as the total amount must increase. So, for change in entropy, total change in entropy to be positive, free energy, that's change in G, Gibbs energy, must be negative. That means for all spontaneous changes, change in G, that's Gibbs energy, change in Gibbs energy must be negative. That's also an important question for why I can jump. So if change in G is positive, the reaction will not take place unless some condition is altered to make change in G negative. Usually, supplying heat to the system by raising the temperature is the kind of conditions that you will alter. So if change in G is 0, then the chemical system is in a state of equilibrium. Now this happens when both change in heat and change in entropy are negative or both positive. The factors that affect entropy is temperature, because temperature breaks the bond and make the particles disorderly move in disorderly motion or something. Then we have change in state. Change in state from solid to liquid gives them freedom to move, and change in state from liquid to gas gives them excess freedom to move apart. So we're through with energy and chemical reactions. Let's move to chemical equilibrium. So dynamic equilibrium is a state of a system where there is no observable change in the properties of the system with respect to time. So dynamic equilibrium involving physical change is called physical equilibrium, while that involving chemical change is known as chemical equilibrium. So chemical equilibrium is a state in which the rates of forward reaction equals the rate of backward reaction. What it means is that the reactants will undergo a change in composition to form the product, and these products will then be reconverted to the original reactants at the same rates. So a chemical equilibrium can only be achieved in a closed system, something to note. Now, chemical equilibrium, since we have talked about it, that reactants will form product and product can be converted back to reactants. That means chemical equilibrium is a reversible reaction. It can go backward and forward. It's important to note that because you're going to see them in your exams. Okay? So a reversible reaction is in dynamic equilibrium when both forward and backward reactions or directions are occurring at the same rates. Alright? Okay, so let's look at Le Chatelier's principle. Now, every reversible reaction undergoes equilibrium under a set of conditions, and these conditions depend on temperature of the reacting system, pressure of the reacting system, and the concentration of the reacting system. So a change in one of these factors will upset the balance of the system and result in a shift of the position of the equilibrium. So Le Chatelier's principle comes to address that and says that if an external constraint like change in temperature, change in pressure, or change in concentration is imposed on a chemical system that was already in equilibrium, the equilibrium position will shift so as to annul or neutralize that constraint. Okay? So recall that for an endothermic reaction, heat is absorbed and change in heat is positive, which means that the heat is in the reactant. But for an exothermic reaction, heat is released, therefore heat is a product. Okay? So if we refer heat as a reactant or product, then we can apply Le Chatelier's principle such that if we raise the temperature of an endothermic reaction, it is like adding more reactants to the system, and therefore by Le Chatelier's principle, the equilibrium will shift to the right hand side, to the product side, and the value of the equilibrium constant will increase. But for an exothermic reaction, the heat is a product, right? So increasing the temperature will cause a shift in equilibrium to the left, while decreasing the temperature will shift the equilibrium to the right. Only the effects of change in temperature can affect or change the value of the equilibrium constant. Other stresses will not. So this is how I ask this kind of question. Remember, we're just doing revision. They can ask you, state Le Chatelier's principle, and you go, Le Chatelier's principle states that if an external constraint such as a change in temperature or pressure or concentration is imposed on a chemical system which is already in equilibrium, the equilibrium will shift so as to annul or neutralize the constraint. Clap for yourself. Then they go ahead and ask to mention some of the stresses. Remember, you've already mentioned them in your law, in your Le Chatelier's principle. So the stresses are change in temperature, change in pressure, change in concentration. If it's a gas, change in pressure. Okay, we have already discussed change in temperature. Okay, let's go into the next one, change in pressure. Now, for change in pressure to affect the system in equilibrium, one of the reactants and products must be gaseous. The total number of moles of gaseous molecules on the left side of the reaction must be different from that of the product. What I'm saying is that for change in pressure to affect the system in equilibrium, one of the reactants and one of the products, at least one of them, the reactant and product, must be a gaseous molecule. And then out of these gaseous molecules, they should not have equal moles, the product and the reactant gaseous molecules. One of them must be smaller or lower than the other. A change in pressure by changing volume. Remember gas laws. Boyle's law, as the volume increases, pressure decreases. So that means for gases, for you to increase pressure, you deal with the volume. So I'm saying a change in pressure or volume will result in an attempt to restore equilibrium by creating more or less moles of gas. So if the pressure increases, or volume decreases, the equilibrium will shift to favor the side that involves fewer moles of gases. And the same thing happens if pressure decreases or volume increases. The production of additional moles will be favored. Like I've said, you go through the lecture playlist and you will see this topic in details. We're just revising, so we're not going to solve problems. We're revising, and when necessary, we give you formulas, and you're going to see more details if you're interested in going to the topic in the playlist for your own good. All right, then we have effect of change in concentration. Now, in an equilibrium system, there is a balance between the concentration of reactants and that of the products. That's why you balance reactions. Now, if more reactants are introduced into the system, the balance is upset, because it's either you're adding it when you add it to the product, reactant is now less. So that balance is upset. In order to annul this constraint, the equilibrium will shift to the right, to the product side, favoring the forward direction, and that will result in an increase in the concentration of the product. Now, but if we remove the product continuously from the system, and that will reduce the product, isn't it? Making the reactant more than the product. Because of this, the equilibrium position will also move to favor the forward as the product side to try and increase the amount of product. This is what most factories use to increase the rate of their reactions. Now, we also have the effect of catalyst. Remember that a catalyst does not change the position of the equilibrium, but it can be used to speed up or reduce the rate of reaction. That's time taken for the system to attain equilibrium. So a positive catalyst will increase the rate of both the forward and the backward reaction by lowering the activation energy of the reaction. Now, Wire could also ask that to explain how a catalyst speeds up or lowers the rate of reaction. You remember we talked about that reactants must collide, and then when they collide, they must have enough energy called activation energy before a reaction can be formed. Now, if that activation energy was high, let's give an instance 1000, the collisions have to be more, should happen a lot of time before it gains that energy to result in a reaction. Just imagine that you're carrying a stone to hit on another stone to form fire. It's not the first time you're doing that will bring fire. Maybe an expert. But if you keep doing it, the heat generated by both stones will increase up to a point where the next one will bring the fire. That's what you can use and compare with this reaction, collisions, and the activation energy. So if you introduce a catalyst into a reaction, how does it then speed up that reaction when we know that these collisions must collide to reach that activation energy? What it will do is that it will go and lower the activation energy. So if the activation energy, like we said before, was 1000, it lowers it to like 200. So the collisions are not going to take that long before it leads to a reaction. That's how a catalyst speeds up the rate of reaction. So if it was a negative catalyst, we should go in there and slow down the rate of reaction. It will go and increase the activation energy. Let's say the activation energy was 2. It would be too fast a reaction. So you want to slow it down. There are reasons why you slow down reaction, maybe to observe all the changes. You send in a catalyst that will go and increase the activation energy, and by so doing it lowers or it delays the time taken for reactants to be formed and product converted back to the reactants. That is how a catalyst affects a chemical reaction. Okay, so in summary, when an equilibrium system is altered, the equilibrium is re-established when one of the stresses of change in concentration, change in pressure, change in temperature, when you apply one of them. Okay, so remember again that among the 3 stresses, only change in temperature can change the equilibrium constant value of the system. Equilibrium constant is K. Other stresses like pressure and concentration does not change the equilibrium of the system. So equilibrium constant remains unchanged except when it's a change in temperature constraint. Okay? Now, if you are calculating equilibrium constant, remember that equilibrium constant is by a certain rule, the law of mass action, which states that at constant temperature, the rate of reaction is proportional to the active masses of each of the reactants raised to the power of their coefficients. That's what you are going to use to calculate equilibrium constant. Okay? So you divide the products of the reaction by the reactants of the reaction, but those mole numbers that were there are going to become power raised to the power of those mole numbers. Those are the coefficients. I'm trying to say, let's say we have N2 plus 3Cl2, those are reactants, yields 2NCl3, that's a product. Equilibrium constant is product all over reactants and raised to the power of their coefficients. What are the coefficients? N did not have anything, so it's just 1. N2, no mole number. But Cl2, there are 3 because it was 3Cl2. So the coefficient of Cl2 is 3. I'm just trying to explain raised to the power of their coefficients. But it's product all over reactants. So we go product. NaCl is a product. It was 2NaCl3. So the coefficient was 2. So I say NaCl, the product, raised to the power of its coefficient 2. All over the reactant. The reactants are more than 1. So I say N2 plus C. N2 doesn't have a coefficient, it's just N2 gas. So N2, I don't raise it to the power of anything. Plus, it was 3Cl2. So Cl2 has a coefficient 3. So I write Cl2, I raise it to power 3. So that's product all over reactants, and all of them raised to the power of their coefficients. You put the values as given in the question. That's if N2 was 0, NCl3 was 0.25, you write 0.25, and then all over N2 was 0.15 plus Cl2 was 0.015, and then you have your answer as 1.51. I'm just telling you how to calculate equilibrium constant value. Now we move to water. Water is one of the most common substances known. It's a good solvent for many substances, and it rarely occurs in its pure form in nature. The different sources of water: rainwater, spring water, well water, lake water, and seawater. But rainwater is the purest form of natural water because it is formed as a result of the condensation of water vapor. Okay? Spring water contains, considerable amount of mineral salts, but very little suspended impurities like dust and bacteria. So it's also a good source of drinking water. Well water contains a lot of clay and other mineral salts. Lake and seawater contains a lot of dissolved air, mineral salts, bacteria, and organic matter. People drop dead bodies there. So these water bodies have to be specially purified before they can be used for drinking. and all the types of natural water are in constant circulation, which forms a water cycle. Water can be hard or soft. Hard water does not form leather easily with soap because it contains a number of dissolved salts, and most importantly, being calcium tetrahydrosulfate 6 CaSO4, magnesium tetrahydrosulfate 6 MgSO4, calcium hydrogen trioxocarbonate 4 CaHCO3 2 are the dissolved salts. Now, water can acquire hardness when it dissolves gypsum, the CaSO4 we talked about, that's calcium tetrahydrosulfate 6, or limestone, CaCO3, from the soil over which the water flows. There are two types of hardness of water: temporary hardness, which is hardness caused by the presence of dissolved CaHCO3, which decomposes on heating, and it can be removed by boiling and also by using a calculated amount of slaked lime, calcium hydroxide, or lime water. Also, we have permanent hardness, and is a hardness caused by the presence of calcium and hydrogen ions in the form of soluble tetrahydrosulfate 6 and chlorides. It can be only removed by chemicals such as washing soda, caustic soda, and permutites or zeolites. That's ion exchange resin. It's an objective question. Permanent hardness can be removed using an ion exchange resin like permutite and zeolite. What are the advantages of hard water? Hard water tastes better than soft water because of the dissolved minerals in it. So the calcium salts present in hard water, when taken in by animals, help to build strong teeth and bones. And hard water helps snails and crabs to make their shells. These shells are mainly made of calcium trioxocarbonate 4. But the disadvantages of hard water: for washing, hard water requires a lot of soap before it can form leather. So the disadvantage is that it wastes soap. Okay, so soft water is ideal for washing. Hard water causes fouring of kettles, those white four-like layers, coatings on your boiler rings and your kettles. It's caused by hard water, so it can coat and spoil the ring. Now, hard water is not used in dyeing and tanning because the salts that are dissolved in it will interfere with the modes of action of these processes of dyeing and tanning. Water can be polluted, okay? And the common pollutants are refuse and sewage, industrial and agricultural wastes like chemical waste from industry, and crude oil spills. How can we control water pollution? Refuse should be buried or burnt in incinerators, and sewage should be processed, treated, and converted to useful fertilizers. And chemical waste should be converted to harmless biodegradable substances before being dumped in the sea. And safety measures must be implemented to prevent crude oil spills. And then strict laws must be passed to control water pollution by industries, individuals, companies, etc. What are the physical properties of water? Water is a clear, colorless, tasteless, and odorless liquid with the following properties. It has a boiling point of 100 degrees Celsius and freezing point of 0 degrees Celsius. It has a maximum density of 1 gram per cm cube at 4 degrees Celsius and neutral to litmus. Remember what is called the anomalous nature of water. Water does not expand between 0 to 4 degrees Celsius. So at 4 degrees Celsius is when it starts expanding, and that is called anomalous nature of water. Okay, so the chemical properties is that sodium, potassium, and calcium react with cold water to form alkalis and will liberate or give off hydrogen. Magnesium and zinc also react with steam to liberate hydrogen and form oxides because of the oxygen present in water. That is a steam. Also, water does not react in any form with copper. Does not react with copper, does not react with gold, it does not react with silver, does not react with mercury. That's why you can use gold outside without worrying about rusting, because water will not react with them. Remember, what causes rust is hydration. The chemical formula for rust is hydrated iron 2 oxide. So water can easily cause, because it causes metals to rust. Now, what are we using water for? You already know that for domestic purposes. That's laundry, cooking, bathing, drinking, cleaning. But water also dissolves mineral salts, which are taken in by plants. So it's also useful for plants. And it's used as solvent in the manufacturing industries. Distilled water is used in the manufacture of drugs and blood infusions in pharmaceutical companies. Then factories use water to cool their machines. Now, how do we supply water to township? Pipe-borne water is prepared in a water treatment plant, and this water is usually germ-free, but it contains mineral solutions, solutes like sodium chloride. So water from rainfall or river or lake are stored in reservoirs. Now, this water is purified by various methods. The first being coagulation or flocculation. Now, water is put in a reservoir, and then it is made to settle, or something added to make the solid particles inside the water, the tiny particles, come together and form bigger clumps, so that by the time you want to pass that water through a sieve, the bigger clumps will stay on one side and the water passes through with less impurities. That's coagulation or flocculation stage. Then we have that's when screening to remove suspended dirt comes in. Then we have sedimentation. That's the next stage, to remove the dirt particles after coagulation. So we have to pass it through a sieve, and then the water goes out, and then the coagulated dirt is collected in one compartment and removed. Then we have aeration. That's when to remove dissolved gases or odor. Aeration. And then filtration. Filter it. And then disinfection. We use chlorine mostly, or potash alum, or iodine, fluorine, calcium hydroxide to disinfect, but mostly chlorine. So how is this done? Untreated water is first passed through large settling tanks where potash alum or sodium aluminate are added to cause coagulation. Okay, so the impurities will clump together to form big particles of dirt, or we call it flocks, FLOCS, which will settle down rapidly. When they were particles, they were still suspended in the water, but now that they're formed into bigger particles, that will now settle to the bottom. Okay, so the water is then passed through a filter to remove the remaining fine particles of dirt. The water is then treated with chemicals like chlorine to kill germs. And finally, the treated water, which is now clear and free from germs, is stored in a reservoir and distributed in underground pipes to the town for use. That's how water is treated and supplied to the township. Now let's look at solutions and solubilities. When a solid dissolves, its individual atoms or molecules or ions interacts with the solvent, like water, they will become solvated and will be able to diffuse independently throughout the solution. Now, if the molecule or ions collide with the surface of a particle of the undissolved solute, it may adhere to the particle in a process called crystallization. This process of dissolution and crystallization will continue as long as excess solid is present, resulting in a dynamic equilibrium. I'll explain all this. We know solute plus solvent will give you solution. The forward process is called dissolution. That's solute plus solvent undergo dissolution to give you solution. But if you want to convert solution back to solute and solvent, then that's crystallization. That's what we're talking about there. So crystallization refers to the formation of a solid with a well-defined crystalline structure. And then we said when a solid is added to a solvent in which the solid is soluble, okay? Solute particles leave the surface of the solid and become solvated by the solvent. They dissolve into the solvent. Now, initially, to form an unsaturated solution. What I'm saying is, you put 1 cube of sugar into a cup of tea, it dissolves and finish dissolving. It needs more. It's unsaturated. Okay? Now, when the possible amount of solute, like the sugar, has dissolved, the solution becomes saturated. If you dissolve and add more sugar till the water molecules take up sugar and all the water molecules are filled up, it can't dissolve more again. It becomes saturated. If the excess solute is present, as the excess sugar that in the tea cannot dissolve again, the rate at which the solute particles leave the surface of the solid will be equal to the rate at which they will return to the surface of the solute. You stir it. If one dissolves, another one that was already in solution will crystallize back. So you still see the solute at the bottom of the cup of tea unchanged. Maybe one dissolves, another one crystallizes back because it's full. The molecules of water has all been taken up by the solute, the sugar. Okay, so a supersaturated solution is that one where you filter off the solute that did not dissolve anymore and leave a clear liquid that is saturated. Okay, so solubility is the maximum amount of solute that can dissolve or that can be contained in 1 dm cube, that's 1 liter of a solvent at a given temperature. Solubility, what I'm saying is how much sugar, for instance, can be dissolved in a particular amount of water, like 1 liter, at a given temperature. That's solubility. So a saturated solution of a solute at a particular temperature is one which contains as much solute as it can dissolve at that temperature in the presence of undissolved solute particles. How you will know a solution is saturated is that you will see some particles inside that cup or whatever that is not dissolved anymore, undissolved. So I've eaten, I'm satisfied. You see a plate of food. To know the person that is satisfied, you see that in front of him the food is still remaining. It can't eat anymore because it's full up, it's filled up, it's full. That's what happens to solutions. When a solution is filled up, it can't dissolve any more particles. Then inside that solution, you see undissolved particles. You see inside your tea, you see sugar at the bottom of the cup that did not dissolve. That shows that the water has taken up enough sugar, it can't dissolve anymore. So what you do, you can add a little more water, or you can heat that tea again. Increase in temperature will increase the solubility of that, or adding more solvents can also do that. So I'm saying we have 3 degrees of saturation. Unsaturation, that's the cup of tea. Now you're adding sugar, it's not enough, you want you to add more because it can still dissolve more. That's unsaturation. And it gets to the point that it is saturated. That is when you have the excess sugar that cannot dissolve anymore in the cup. That's saturation. That's the second one. And the third one is supersaturation, where you filter off all the undissolved solutes, and then the clear liquid that is left behind is a saturated solution. Those are the 3 degrees of saturation. So we have the solubility curve or graph. Now, if the solubilities of a solute in a given solvent are plotted against their respective temperatures, you have a solubility graph or curve. That means it shows the effect of temperature on the solubility of a particular solute. That's to say, the temperature on one side with the vertical and the solubility on the horizontal of the graph is a solubility graph. So if you're using sugar, for instance, I put sugar in water of 0 degrees or maybe normal temperature and maybe 40 degrees Celsius, and then try to dissolve it. See how much it dissolves, record it, plot it in diagram. Increase the temperature to 50, record the different solubility you have and put it on that graph. It will end up forming a curve, that solubility curve. So in a solubility curve, most solids increase in solubility when you increase the temperature. Take notice of our equation. But gases reduce in solubility when you increase the temperature. So for solids, there is increase in solubility as you're increasing the temperature, but gases, the solubility will go down, will decrease when you increase the temperature. Okay, gases are moisture, as they are still liquids, but in gaseous form, very tiny particles. So if you increase the temperature, it becomes tinier in particles. So not enough moisture to even dissolve as much as it would have dissolved before you increase the temperature. That is why. Now, the factors affecting the solubility of a solid in a liquid are temperature, nature of the solutes, nature of the solvent, volume of the solvent. And how can a saturated solution be made to dissolve more solutes? Like I'm saying, you put sugar inside water and you stir and keep adding sugar until there's a point where some sugar can't dissolve anymore. How can you make such a saturated solution dissolve those sugar that is left at the bottom of the cup? Number one, increase the volume of the solvent. Like I said, add more water. It's common sense. If you add more water, you see the salt dissolve more because new molecules of water have been added that does not contain the sugar, and then the sugar can dissolve into those ones, and then maybe the sugar all can dissolve. Or you increase the temperature of the solution. Just carry the tea, return it into something and heat it a little. See, it dissolves more. So those are the ways you can make a saturated solution dissolve more solutes. Increase the volume of the water or the solvent, or increase the temperature of the solution.